any kind of structure you can uh, model and analyze and design in SAP 2000. But there are some specialized software like ETABS, which is mostly focused on designing a building. Similarly, there is a software CSI Bridge, which is also more biased to design of bridges. And some of you must have used Stat Pro. So if you have the idea of SAP 2000, it may indirectly help you in operating Stat Pro as well. So after giving this brief introduction, I would like to start my presentation. So the presentation topic is seismic analysis of building using SAP 2000. I hope all of you are BTech students, and uh, you will be there. Is definitely you are covered RCC design, in which you must have learned uh, how to design beams, columns, foundation, beam column joints. Maybe beam column joints are not covered. So uh, okay, so my coverage will be to how to analyze the building, how to obtain the design forces. Now I will take each point in very detail. So if you know for what forces you need to design each element, the designing becomes very easy, right? So I'm in this slide, I think is covered related to building design. First of all, like modeling aspects. So uh, you must have, if you have not modeled also, you must have analyzed small beams or small trusses, right? Maybe you have learned moment distribution method, slope deflection method for solving a simple frame. So, but if it is a very complex frame or it's a 3D building, it won't be possible for you to manually analyze it or manually design it. So we take the help of softwares like SAP 2000 or ETABS, and the model which we use in practice, like whatever consultancies are doing. So they are doing all the linear model. So basically there are uh, linear model as well as non-linear model. So more realistic is non-linear model. I will go into this more detail in next slides. So non-linearity, as it is shown, can be because of geometrical non-linearity as well as material non-linearity. Now, once the structural model is prepared, so you are knowing what, like, let us consider a person has given you a plan for designing a building. He wants his building to be designed. So based on that, you will create a model, maybe in any analysis softwares, and then after that, you need to know what kind of loads are going to act on the building. It depends upon the region which you are considering. If it is a region where snowfall is very extreme, you need to take that into account. For example, if we are designing for Siliguri, so we may not require this snow load. So basically, all loads are categorized into two basic subheads. Like first one is static analysis, static loads, which the dead load, live load, snow load, rainfall load, etc. comes into static, and dynamic can be earthquake, wind, or the forces due to water in the river, dam, barrage, etc. And my focus will be in earthquake analysis because I'm working on earthquakes, so I have a better knowledge in earthquake in comparison to other like wind or uh, uh, the river water. So these are the this comes into dynamic loads. And third one is once you know the loads, your model is prepared, you need to design the building. For designing the building, whatever we have learned or some of you are going to learn in your RCC design, concrete design course. So we do gravity design, which is done using IS 456-2000. So there are some international codes for doing each country has its own gravity design codes. For example, US European code is EC8. Similarly, the American code is ACI 318. Now here comes the another branch of designing called seismic design, in which We cover earthquake as well, in addition to the gravity load. So if you are conversed with, if you know how to design by using IS 456, it will be very convenient for you to uh, design it for seismic loads as well. Now the loads we take from IS 1893 and we design by using IS 13920. And if you are looking for American code, it is AC 716, and if you are looking at European code, it is EC2. So these are very basic details. So let me start from the structural model. So structural model, I have given the basic two heads as okay. So linear model and non-linear model. Okay. So linear model. Now everyone has analyzed a cantilever beam, I suppose. Uh, so if we'll see the first diagram where I've shown some cantilever beam and then a lateral load is applied, there will be some deflection in it. So from this, for this small model, what we can do is we can generate a stiffness matrix. Or very basic is how we can know what is the stiffness of this member, right? So if you'll say that there's a uh, cantilever beam and load is applied at its free end, so there what will be its deflection? Its deflection will be WF cube by 3 WL cube by 3 right? So using that, what we can do, we can obtain the stiffness of this member. What will be the stiffness of this member? The stiffness of member will be force divided by deflection, right? So this member, if we are considering only the bending stiffness, so its stiffness will be uh, 3 EI by L cube. So we can totally define this structure in terms of this stiffness parameter. So the stiffness of this member is 3 EI by L cube. So now if you see this 3 EI by L cube, there are few terms like E is there, I is there, and L cube is there. So E defines its elastic modulus, I is the uh, and I can be obtained by using its cross section, and L is its length. So if we are knowing these three parameters, we can totally define this small cantilever beam. Now, if we try to interpolate or extrapolate into this entire 3D building, so this 3D building is also can also be analyzed in the same pattern, like analyzing a small cantilever beam and analyzing a critical 3D structure is also same. Like we know, if we know what are the forces coming into this building, we can create a stiffness matrix for the structure. We do not know how to create as in this at this time. So if we know what are the forces coming into the structure, and if we know the stiffness matrix, so we can easily know what are the deflection at the various points. So using that, we can design the structure. So I have not written the equation here, but the equation will be F equal to Kx, where F is the force, K is the stiffness matrix, and X is the deformation deflection at various points. So if we know the stiffness matrix, there are three components. If we know force, stiffness, and third one is deflection. So these three things entirely define your structure. And I already said that K, the stiffness is dependent on parameters like Young's modulus, uh, length, and I value. Okay, so uh, I will discuss the first portion F in the next slide, but before that, let's go to the model. So I already introduced in the last slide that model can be linear model or non-linear model, and your linear model is is same as designing a cantilever beam. So what you need to know what is the elastic modulus, what is the force. Okay, based on that you can entirely analyze the structure. Fine. Now if it is a non-linear model, because we know that every material is non-linear in nature, but we idealize it for analysis purpose for our study. But actually a model can be model, any model or any material is non-linear in reality. So in case of buildings, nonlinearity is basically because of two main things. First one is material nonlinearity, where I've shown here the stress strain curve for concrete. So this is for M30 concrete. Here you can see that the initial portion, if you'll go from 0 to 20 or 0 to 30, these are more or less linear in nature. So from this only, for linear analysis, we use only this linear portion. But if the structure is subjected to excessive forces, for example, in case of a very large wind or earthquake, the material goes beyond its elastic range, and it goes beyond its elastic range, and material behaves in non-linear way, and its stress carrying capacity can decrease, its deflection can be very huge. So this material non-linearity takes into account the non-linearity of the structure in one way. So if you are designing for very large loads, for example earthquake, you need to consider this material non-linearity as well. Now another non-linearity is considered by its geometry. For example, let's take this again. Let's take this cantilever beam where undeflected shape is shown in the left, and then deflected shape is shown in the right. Now let us consider there is only P. P is the axial load in the column. For example, you have a column and it only axial load is subjected to it. So we know that only compressive load will be there, right? There won't be there will be only axial load that is compressive in nature, right? Now let us consider some earthquake load is also acting in it. For example, V is also acting. So what will happen is, in addition to axial load, there will be moment generation as well, right? And its shape is also changed, and this change in shape, like let's can I see, if you see the deflected shape, what will be the forces in it? The forces we know in the deflected cantilever beam is, first one was axial force, right? Second one was the moment due to V multiplied by its length, right? Moment at the base will be V multiplied by length. But there will be another one force which we are not aware of. This force is generated because of the deflected shape of this model. For example, this P is acting, and which has and the beam has already the column has already deflected by delta. So this delta and P will also cause a moment. P and delta will cause an additional moment. So this we call as, because of the change in geometry of the structure, this additional load will be created, right? So this is also a source of geometrical nonlinearity. There is much detailed things, but I'm covering only the broad headings. Okay, so these two are also to be considered. If we want the realistic analysis of any structure, we need to take all this into account. But in practice, what happens is we only consider the elastic portion, and based on that, we design a structure. But if your structure is of great importance, like 50-story or 100-story building, and elastic analysis only won't work. So we need a nonlinear model. Okay, so I will briefly introduce how to include nonlinear model in a structure. But before that, let's go into, like, once we have created the model, we need to know what are the loads acting on it. Okay, so we know the loads can be because of its self weight, some live load, snow load, and earthquake or wind load. Fine, we know what is the dead load. So let's go to the earthquake load. Earthquake load can be applied in a various ways. So we know that during what happens in the earthquake is uh, ground will start shaking in all directions, like two horizontal, one vertical, as well as the ground starts rotating. So there will be movement along all 6 degrees of freedom. So I've shown a time history data here. So this is the earthquake time history of one of the earthquake I've taken, for example. So the building starts shaking in a very random manner, very irregular manner, right? So we need to actually apply this load to the structure. So uh, let us consider this is the acceleration time history. So building will start accelerating, and this acceleration changes in a very small of time. For example, 0.005. In this small instant of time, the building start its movement very haphazardly, right? So we need to make such an arrangement that this complex load will be considered in the analysis of building. So for that, there's a very basic method called, I have given here point as point one, earthquake load. In subhead of earthquake, I've given the subheading one, which is equivalent static method. So in equivalent static method, what happens is uh, the this complex time history load is converted into very basic load and is applied into the structure. So how uh, it's done, I'll explain through SAP2000. But the method is called equivalent static, where the code has given a very basic way by which we can account this earthquake load without a requirement of any earthquake time history data. So by earthquake time history, I'm talking about the acceleration time history, because a ground accelerates in every instant of time, and by using, if I have to say in a very basic way, it may not be exactly correct. So if we have acceleration and we have the inertia of building as mass m, so we can obtain the force acting at the base of structure as force equal to mass into acceleration. So we can know what is the force acting at the base of building, right? So if we are knowing what is the force at the base of building, we can distribute into the various floors, and we can analyze building for that, right? So now, first process is equivalent static analysis, and another second one is the uh, response spectrum analysis. Okay, this is also another way of accounting for earthquake loads. So now, if you'll see this earthquake time history contains a very randomized data. So if some of you must have read Fourier transform, all of you must have actually read the Fourier transform. What we do in Fourier transform is we uh, unbind mm, any data, any time history data into very simple shapes. Like we break a complex signal into its sine and cos functions, right? So if we break into a complex time history function, we can break into a number of sine functions having different periods as well as different amplitudes, right? So if we'll apply, okay, so let me briefly explain you what is response spectrum. This complex shape is everything you need for designing a building for earthquake, whether it's equivalent static method or whether it's response spectrum method. This response spectrum shape is the everything which you need for designing a building. So you may not understand this time, but I will try to briefly explain you what is this. So let us consider you have applied this ground motion, this time history data into a simple cantilever beam. Okay. So when you apply into simple cantilever beam, what will happen? It will shake according to the ground motion which we are giving at the base, right? So once it shakes, it will also create a similar kind of deflection at the top of the cantilever beam. Okay. Okay. Let me show you with a small diagram. Let us consider this cantilever beam. Okay. Now, if we are applying some force here, some force P at the cantilever beam from this left side. Okay. If you are applying some earthquake time history data, very accurate data, if you are applying from lateral direction. So if we have earthquake, we may not be able to apply here, but we gave the same time history data at the base of the building, right? So let's consider we have given force from lateral direction at the base of the building. So at the top, the building will also vibrate haphazardly with the time, right, during earthquake. So what will happen that, okay, so yeah. So the top of the cantilever column will also vibrate in haphazard manner. But at some of the point, we will obtain a peak value, right? There will be a peak displacement of the cantilever beam at its top, right? So the cantilever which we had taken is having some time period. Like every building or every element has some time period. So there are a number of time periods. So all models are having a fundamental time period. So since we have taken 1 degree of freedom system, single cantilever beam, for example, so if you are applying the time history data at the base of the cantilever beam, it will vibrate. But at some instant of time, it will have some peak value. Now, if we are repeating that into a number of different single degree of freedom cantilever beams or single degree of freedom systems, it will have different deflections, right? Because some cantilever beam may have 1 meter height, some may have 2 meter height. Based on that, we can vary the time period of that model, and we can check what is the peak deformation acting uh, at its top. We can also see what is the peak acceleration acting at the top of that a single cantilever beam, right? So if we plot the maximum acceleration uh, at with respect to the time period of that single degree of freedom, the diagram which is prepared is called response spectra. Actually, for every earthquake, the response spectra is having a very haphazard shape and very different, very unique shape. But for design purpose, the code has given a very simple, rather saying simplified spectra for designing the structure. So if you are not understanding all this what I've said, then also there's no problem because it's beyond your scope at this time. But you need to know this is the response spectrum is everything you need for designing a building, whether it's equivalent static method or whether it's a response spectrum. There's a third method also, time history analysis, where we feed the actual time history data, actual earthquake data at the base of the building, and we design that building. Okay. So going on to the next slide. Uh, Now we have known model can be linear, nonlinear, loads can be applied in a various manner. And let's see the third one. Third one is gravity design. Sorry, design. Design can be done for gravity loads and can be done for seismic loads. Now, if we design a structure for only gravity load, we call that as ordinary moment resisting frame because we are designing it for some axial force, some moment, and some shear force. And so this we call that as ordinary moment resisting frame. Now, if you design it for seismic load or wind load by using IS 18930, we call that the design building as special moment resisting frame because it is taking into account the various ductility requirement as well as the earthquake loads. So we call that kind of building as SMRF building. So I'm not going to cover the design aspect because you are going to learn in your RCC course. So, uh, but this seismic design and SMRF, I will explain you when I will take in the SAP model into consideration. I hope all of you have started your SAP 2000 software, and if not, please start it because I'm starting the SAP 1000. I will ultimately explain the various method of accounting earthquake load and modeling of building. You can model a very simple model to very complex model if you know the basics of any of the software. So here since I'm very conversed and I'm working on SAP 2000, so uh, I will use SAP 2000 to explain you how to model, how to analyze, and how to design a building. A software, a building or any structure can be designed in the software also, but the software software gives the design values. For example, you're designing a column, so a column can be designed by software. You can also manually design it, right? But so we know that software, it's a black box. We do not know what is uh, mostly we do not know what is the software doing inside, and it also every time you design it, it will give a same result. But we know design is our choice. We can give a larger section, we can give smaller section, we can choose a die of reinforcement. So it's more flexible for us to design, more flexible, more convenient for us to uh, design. It will better if we manually design. So most of the consultancy, what they do is they analyze the building, but they analyze the building, they obtain the load from the software, but they manually design it because there's much flexibility in terms of assigning sections to that components of the building. Okay, so let's. Uh, uh, I'm covering. I've told you that there are three ways we can account or we can assign earthquake load into the structural model. So the first model I'm taking, first method was equivalent statics, second is response spectrum, third one was time history analysis. So I'm starting from equivalent static analysis. Before that, I'll go to SAP 2000 and I'll explain you in basics how to model a very simple structure. So everyone, if you have installed SAP 2000, please open it. So I've also opened your SAP 2000 model here. Okay. So yeah, so this is the, if you, okay. Yeah, this is the SAP 2000 initial screen where you can find the number of panels here at the top. And I'll explain these commands in a very brief way when I start modeling. So let's first consider tab here. This keeps a new model. So there are a number of default model into the SAP. As already told that SAP is a very versatile software, can be used for designing various kind of structures. So we are looking here at for building. So while analyzing the model, you need to assign what units you are taking into your study. You can change anytime the units because while in the process of designing or analyzing building, it will ask again and again what unit you want to see. So I've initialized here into SI units, kilonewton meter, and see there are various templates, predefined templates which are given. If you want to model in a very short amount of time. So I'm starting with the 2D model. We can do it in a 3D model also. Okay, so what? Let's go in 3D model. Okay, because if you know 3D, you can also easily define 2D model. So let's go into 3D model, and 3D model is more realistic. So here, okay, before that I forgot to say one thing. So if there's any doubt to anyone, you can type in chat section and then I can reply for that. Okay. So once we have, so from new model, once we have selected a template, we can start from grid only also. But I've selected here a 3D model because I'm trying to design a 3D building. So 3D, well, if you already know the plan of the building, so what you can do is, for example, let us consider this is the plan of building, right? So your plan can be very complex, but you need to you need to make grid out of it. So XY grid, and then based on that you can make a plan of the building in the software mode. For example, this I have taken for one of the buildings at IT Partner. So this is a residential complex, and its final model will look something like this. So this is one of the views. Uh, okay, so okay, I was showing you the SAP 2000 here. Okay, so once we have selected 3D grid, we need to know what is the number of, we need to assign it, what is the number of stories, what is the number of bays in X and Y direction, what are the bay length, you can see here, right? So story, height, bay length, you can number of assign. But if you can see at the this figure, it's a very box kind of structure, but your structure may not be such kind of simple structure, right? It may be having very complex shape. Excuse me. So you can use grids, custom grid spacing for assigning the grid here, and then you can assign grids in X, Y, and Z direction, and accordingly you can make the plan of the building. So here I'm assigning very. I will show you for a very simple building because everything starts from simple. So let's consider only three story building. Story height 3 meter. Number of bays in X direction is 3. Number of bays in Y direction is 2. And let me keep bay width in X direction is 5 meter. Bay width in Y direction as 5 meter. Okay. So using that, or let's consider a very simple model is created. 3D model is created. Okay. So here we do not know what is the beam size, what is the column size. It has created a default model by assigning some default properties. So once we have this, what we need to do, we need to define what is the material which we are going to use and what are the initial section, because if you want to know what loads are acting on the structure, we need to know what are the members, because self weight comes from the member, right? So this is a basic model, and we can we need to assign lots of property to this. This is nothing. This is just a grid. So we need to assign whatever we can for design for modeling and realistic building. Okay. So most important here of the tab in this top section is define. So this is edit, view, define, draw, assign. So define, from the most important are define and assign. From define, we can define whatever we want to define. We can define material properties. Uh, we can define material properties. We can define the section details. We can define non-linearity. Can define, and then assigning is the loads. What additional load we want to assign to the structure. So let's go to the defining. So this phase is called analysis phase, because let's consider building is planned and then you need to analyze the building. For that, you need to model the building. Okay. So let's go to define, and defining a building starts from defining materials. So here there are two default materials which are not as per the Indian code. So let's go to defining a new material. So most of the structural building are very basic building. I'm considering here RCC building, which where the materials are concrete and reinforcement. So it has also given a code, predefined materials for various countries. So let's select India and then let's go to concrete. Okay. So once we know this, we can go to M30 or various other things. So I'm selecting M30 and then let's do okay. So our model is created. Material. Now let's one more define the reinforcement also. So you can see here the steel is there. So this is for assigning the steel section like IS, JB, ISMB, something like that. But if it is RCC building, reinforced concrete building, so we can go to rebar. Rebar is nothing but technically for reinforcement. So reinforcement, and then it can also ask what reinforcement you want. It's a mild steel, HYSD bars. So these days only HYSD 415 and 500 are used. So I'm using HYSD 500 for here for this purpose. So HYSD 500 rebar I've created. So I've defined these two materials. Okay. Now once the material is defined, you can go to section properties, right? So from here we are defining the basic section, because see, we are designing a building, but for designing the building we need loads. So for obtaining loads, we need to know what loads are acting. The most basic load is dead load, and dead load comes from the self weight of the building, which depends upon the size of the member. So we are giving a trial sections. Okay, so section property, frame section. So let's go to add new property, and then you can select what material you want. So since you want concrete, so we'll go to concrete and then rectangular section. So once we go to rectangular section, we can assign some name. Let's assign it as a column. Okay. So column, and then it's considering we are giving the size of column as 500 by 500. Okay. And then we can assign material, which we had just created. So M30 concrete, and then you can define reinforcements also here. So this is the trial reinforcement here. Now, rebar material also we had created HYSD 500. So since only we have created one material, so only one material is shown here. Okay. Now we can see this section can be for beam and column. So let's since we have written here a name as column, let's do this as column. Okay. And reinforcement can be rectangular, circular. We can assign from here, and then clear cover, number of longitudinal reinforcement in both the direction, and longitudinal bar size. So this is not for Indian code. This is a different notification used for different countries. So we use for our purpose 16D means 16 mm dia. But for other cases like 9 doesn't mean 9 has 9 means 9 by 8 inches. So something like that. So for our Indian purposes, we use the symbol D. So let's use 20 mm dia bars as longitudinal bars, and in case of confinement bars, which is stirrups, So let's go for 10 diabars. Okay, and this is the reinforced spacing of the confinement bars. And we also know that uh, uh, we can assign reinforcement as a two-way or three-way, stirrups as two-way or three-way, uh, sorry, two-leg or three-leg stirrups. So here I'm giving a default 3 by 3. Okay, and you can assign, you can check at the end. There are two options: reinforcement to be checked or reinforcement to be designed. So reinforcement to be checked means this reinforcement you are assigning, the software, once we when we'll go to designing phase, it will check only, like it will only check whether the reinforcement provided by you are okay for the assigned loads or not. And another, in the second case, reinforcement to be designed, in this case what happens is, uh, based on the load, the software will calculate what are the design force, which are design forces, and based on that, what are the optimum reinforcement required. So software will design for you. Okay, so we can do anything, because since we are going manually, so we can select any of this, right? So I have assigned a column section, and let's let's again assign one beam section also. To add new property, I will go to concrete again, rectangular. This is the same process. I am assigning the properties of the beam. Let's give as depth as 500 mm, and width as 300 mm, material as M30 concrete, and rebar material is HYC 500, beam. And in case of beam, it does not ask reinforcement. It only asks the cover, concrete cover. So let's assign 0.03, 0.03. Okay, and if
Hello, hello, Ravi sir. There is no audio actually. Hello, 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 Mr. Ravi sir. Can you hear me? Hello. No audio coming, sir. No audio coming, sir. Hello, hello. हाँ सर, कोई ऑडियो नहीं आ रहा था. हेलो. Yes, please check. Okay. It's no audio, sir. Now also.
Hello, sir. Hello. Hello.
Hello. हाँ सर.
more presentation. So here I'm canceling this, and then I'm again start from shell. So here we are assigning some area section, whether to be applied to slab or to walls. So
in shell there are various properties. So here we are using thin shell, and we have given uh, dimension or thickness of 250 mm. So slab are generally kept linear, so it kept elastic. So slab need to be designed manually, and then slab need to only model to the structure. We can model a beam and column for nonlinear loads also. It can, but slab are generally kept elastic, because I will explain you like why we go to elastic design rather than non-linear. It carries a number of advantages. First of all, if the codes IS 1893 or IS 456, the design is entirely linear analysis. So while doing linear analysis, we take some factor of safety into consideration. So here we have assigned some slab section, and then we define some slab section with 250 mm thickness, and we are giving the material as M30. Okay. Now we can also give the material as material HYSD 500. We can give some rebar, default rebar, but these values are not will not be majorly used, because one can design it manually. So you need not consider these things, because if you want the ready-made design from the software, which are more or less mostly not realistic, so you can assign what number of layers you want. You can assign 2 layers, 3 layers, and then you can assign covers in both the directions. So I'm only taking, since I'm explaining you analysis of the building, so let's keep the rebar as default. So it may not vary much, it may not influence much to the weight of the structure. So let's do that, and then keep the slab like this. Now we have assigned section for beams, column, and slab. Now we need to assign that into the grid or the small model we have created. Okay. So let's go to selecting the vertical members. We can individually select each columns, but there are some shortcuts which will let us to select all the vertical members at once. So let's go to select, and then properties. Select, and then we want select lines parallel to some coordinate axis. So if you want to select the vertical members which we are going to assign as column, so we can select select the members which are parallel to z axis. So see, by clicking that, the vertical members are selected. Once selected, we can go to assign, and then assign frame, and then frame sections, right? So frame sections we have created as column and beam, so columns. Okay. So frame section is column applied. So you can see that name is given column to this vertical members. Similarly, what we can do is we can select the members which are parallel to XY plane. Okay. So XY plane, and see all the members in the XY plane are selected. Now we can go to assign frame sections, and then beams. Okay. See, so beams are also assigned. Now we have assigned beams, we have assigned column. Now let's go and assign slab. So for assigning the slab, see, we need to go to a different view, right? So before that, I'm explaining you various things, like this I shade for the new model. These are for opening various other model. These are save and undo, redo, everything. This is for analysis. I'll explain you after a few moments. These are for zooming the structure for a certain location. Okay. Now these are the various views. We can see 3D view of model, XY view of model, XZ. Okay. So for assigning the slab, we'll go to the top view. So for top view also, you can say, since we have model 3-story building, so you can see at various levels. So here, if you'll see here, Z equal to 9 is written. Since we have made a story height as 3 meters, so this is at the top. So 3, 3, 3. So this is at the roof, 9-meter level. Okay, we can go to various level by this up and down button, and this is at the base of the building. Okay, now this is at the roof, and let's assign the slab. So from this panel, we can assign additional members like frames, additional joint, or additional slab, or any area section. So if this is a point, so this gives draw special joint, draw frame, draw quick frame. These three are for frames, and this is for slab. These three are for slab. So I'm using this for assigning a quick area. So by clicking that, it asks like what slab you want to assign. So I have only defined, okay, slab. We can click on slab and then we can assign this. So here we can assign slab like this. Okay, let me change it into a very different view so you'll be able to you'll be able to visualize it much better. So we can play into two different windows to check like what's going on actually. Okay, I have a question here. So somebody has asked, in SAP 2000 software you can use option to define frame. Yes, you can use what option to define the frame? The view revise preferences in the design menu. Have to set okay. So view or revise preferences option in the design menu helps to set that option is there, but I've not gone to design as of now. So we can answer that question in the later sections. In SAP 2000 you can use that option to define frame. So yeah, there's an option here, define, and then section properties, define frame. Okay, so here from here, these are all I think this video is being recorded, so you can refer at any later time to see this. Okay, how I have done that. So I'm again assigning slabs here. Okay, now once we have assigned the slab, we can select this slab, since we need to assign at the other two levels also. So in spite of doing it manually, I'm selecting all the slabs which I have assigned as of now, and then I'm replicating to various floors. Like, so in edit command we can do replication or editing. Okay, so replicate, and then it will ask where we need to replicate. So we need to replicate in the lower floors. So let's do -3 here, and then since we have two lower floors, so I've done minus for going into lower floors, and then since we need to assign it for 2 floors, let's place it 2 here. So see, so slabs are assigned to all these 3 floors. Okay, so this is how we have model structure. Now if you'll see, one additional thing is to check at the base of the building. So we know that the building rests on soil, so we need to actually define soil properties also. But in practical purposes, we need to design buildings into various quick succession, and there are lots of things we need to do for soil. We need to learn for soil. So the conventional design for various residential buildings, a very simple building for 5 to 10 stories, generally soil properties are not considered for modeling a building, of course. So, and in this model you can see at the base of the building hinge is there. So how do we know the hinge is there, or whether it's any other boundary, any other thing? So we can right click on this joint, and then we will be able to see what kind of restraint is applied at the base of the building. So we can see that the restraint is there in translation only, but it can rotate. So what kind of support is this? The support is hinge support. Okay, so I'll cover all your questions after giving this brief description of this model. Okay, so now by clicking, we saw that there's a translational restraints applied. So, but for practical purposes, what we do is we fix all the supports and we analyze the building. Okay, so what we'll do is we'll go to base of the building. So you can see here z equal to 0 is there. We can select all this base supports. See, it's highlighted in both the windows, and now we'll go to assign joint, and then we are going to assign restraint. Now we'll fix all the bases. Okay, so we have fixed the bases, and you can see here the symbol also changed. Okay, now we have fixed the building. We have assigned beam column as per our requirement. Okay, now what we need to do is we have applied dead load. Okay, now we need not calculate it manually and then apply to the structure. Okay, now you need to apply some live load. For that, we need to first of all create what are the loads we are going to assign. So we have created material, section properties, and there are various other commands, but important commands I will highlight for now. So load patterns, what load we are going to apply. So in case of load pattern dead, there's a default called dead, because without dead we can't do anything. So we'll assign some live load. So we'll define a load pattern called live, and then live here, and you can see self weight multiplier. If you go to any other load cases other than dead, it will automatically show 0, which means dead load is only going to take we are only going to take the dead load into we are going to only consider the self weight from the self weight as the dead load. Okay, there are various considerations, like some portion of all live load is also to be considered in self weight in dead load as per the earthquake analysis. But for now, for a very basic thing, in case of dead load, we keep the self weight multiplier as 1, which means we are considering self weight as the dead load, and for live load or any other load we keep the self weight multiplier as 0. Okay, so we have added this. Let us consider one more called earthquake load. I am assigning EQ. Okay, so EQ here as I'm doing for other, keeping it as other. Okay, so I've added others also. See, if you see in this like various loads, dead is there, live load is there, roof load is, quack load is there. So quack load is also another way of defining quack. Why we are not using this, I will assign you in a later portion. So I'm making here as EQ load rather than I'm defining one of the load pattern as earthquake rather than using the default one. Okay, because if you select default one, it will ask a number of code and then you need to assign number of parameters. I don't want to make it complex, so I'm keeping it as EQ and then keeping it type as other. Okay, so these are the 3 loads we are basically going to consider for this model. Okay, so once I have created load pattern, so I need to make various load cases. Okay, in case of load cases, dead is also there. So here in load cases you can change whether you want to consider elasticity linear, you need to make your building linear or non-linear, or you want to make various kind of analysis, because I've told you there are some analysis like time history analysis. I've told you there is some kind of analysis called response spectrum analysis. So in load cases you can set what kind of analysis you want to do. Okay, so I'm showing you this for dead load, and you can, if you want to modify something, you can go here and you can modify. Okay, so if you see here, it will ask the name, it will ask what kind of analysis you want to do. You want to do static analysis, multi-step analysis, response spectrum, time history, moving load for vehicles, and there are various other things. So dead load is static in nature. We need to go in each kind, and then we need to modify that if you want analysis to be linear, non-linear, or non-linear staged construction. Okay, because some kind of construction may continue for few stories, and then for after a few number of years or few number of months, different stage of construction is done. Okay, so I'm keeping it linear for now, and then it can ask load pattern whether you are applying acceleration to the building, whether you are keeping it as a dead. Okay, so here this is for dead load. Now we can go to model. Okay, I will not explain your model for now because it's a different concept. So because see, in load pattern we have defined 3 load pattern. One is dead, another is live, and another was earthquake. So but there's one default which is always created called model. So if you want the properties of building, some dynamic properties of the building, we can see from model, or we can make some change in this load case. Okay, so I'm going to live load, dead load. I've shown you live load will also be linear elastic, and earthquake load also linear elastic. Since I'm doing I'm showing first of all as equivalent static analysis, so the name I'll change here as equivalent. Okay, let's keep EQ only to prevent any confusion. Okay, fine. And this is again static analysis, because in equivalent static analysis I showed you in some slide. This equivalent static method, we are applying the earthquake load in a form of lateral load in a static manner. So that's why it's called equivalent static load. So that is again static force only. Okay, so these are the 3 load cases I have assigned as of now. Okay. Now, but we have created for loads, right? But in addition to, like, we know dead load, live load are there, earthquake load there, but we need to combine it, and then we need to assign, analyze the building for combined load. So we will go to define and then make load combination here, add new load combo, and it can also create default combination, but I'm creating a very uh, two very basic combinations. Let us consider combination one as, we know the combinations are given as 456 as well as IS1893. So the most basic combination is 1.5 DL plus LL. So 1.5 DL and 1.5 LL. So this is the first combination. Let's consider. Let's write the name as of this combination as 1.5 DL plus LL. Okay. Fine. Now let's make one more combination. 1.2 DL plus, you must be knowing about the combination, or if not, you will be able to know it when you will learn the design of structures. So 1.5 DL plus LL plus earthquake. What we are doing, we are assigning some load factor to the building that will impart an additional factor of safety. So 1.5 DL plus LL plus earthquake load. Fine. Okay, so these two load combination I have assigned. So we knew that what loads we are going to apply, but what is the value of the load? Okay, the value of load, we can know what is the live load we can apply from IS 875 part 2, right? For dead load, the sections will itself give its self weight. Now for earthquake load, we need to go to IS 1893. IS 1893 is the code which is generally used for Indian scenario for calculating the building. So this is a plot called seismic zonation map, for whether it's a earthquake load, whether it's a wind map. For every kind of loads, there's a zonation map given in various codes. For this is IS 1893 I'm showing you. IS 1893 is for our criteria for earthquake design of building. So yeah, so this is a zonation map of India. You can see there are 4 colors: zone 2, 3, 4, and 5. So the most extreme case region is zone 5, where we'll expect the maximum earthquake forces. We are in zone 4 in Siliguri, and zone 4 is also extreme in nature. The major earthquakes are expected in Bhuj of Gujarat, and you can see this region as also given as zone 5. So this map is plotted on based on some research as well as the past experiences from the various earthquakes. So based on that, the earthquake is entirely divided into 4 zones, and the 4 zones are given as zone 2, 3, and 4. Based on that, we will find what amount of load will try to know what amount of load we are going to apply in the various zones. Okay, if your building is situated in zone 4, you will take the loads or some factors for zone 4, and then you'll try to obtain what is the equivalent static load, what is the load you want to apply to that building. Okay, so let me go through the equivalent static method. Okay, so in case of equivalent static method, the most basic thing is obtaining what is the force at the base of the building. The force, if you are building, okay, at the base of the building, whatever the lateral force is there, we call that as base shear. Okay, so code has said obtain base shear and then distribute to the various floors. But how to obtain base shear? So here I have denoted base shear by VV. AH is the seismic coefficient, W is the weight of the building. Okay, so if somehow we know what is the weight of the building, we will be able to know what is the base shear we need to apply. So let's consider we know what is the weight of the building. Okay, weight of the building is given by the weight of the various components like beam, column, and slab. If there is wall, then wall also. So if we know weight of the building and if we know AH, the seismic coefficient, it is in percentage, like 1 or 2 or 10, 20, some percentage of the building. Okay, so if we somehow calculated AH, let us consider we have got AH as 0.1, which is 10%, right? So the base shear, the lateral force acting at the base of the building will be 10% of the building weight. Okay. So in that way, we can know base shear. So base shear is the first and the foremost thing we need to know to calculate what is the lateral force. Okay. So knowing base shear requires weight of the building. We can know what is the weight of the building since we know the material properties of our members. Okay. We have also assigned what is the probable size, what is the trial sections. Okay. So after knowing the weight of the building, we need to know what is the AH. AH is the seismic coefficient. You can, if you'll see the right hand panel of my slide, okay, here seismic horizontal base shear coefficient AH is given by Z by 2 SA by G I by R. Okay. So SA by, first of all, Z. So Z is the zone factor. Okay. Zone factor, there are different zone factor for different zones. For example, I've shown you 4 zones, zone 2, 3, 4, and 5, right? So code has given zone factor for various zones. So for example, in zone 5, which is the more extreme zone, the factor Z is 0.36. In our case, in our Siliguri, the zone factor is we lie in zone 4, so our zone factor is 0.24. You can get all this information from IS 1893. So zone factor varies this seismic coefficient based on what zone or building is being designed. SA by G is the seismic coefficient. SA by G is a factor which we obtain from the response spectrum. I already told you that if you know the response spectrum, you will be able to entirely obtain what are the design forces. So see, if you'll see the diagram, this plot gives SA by G versus natural period. So natural, our building is having some natural period. Let us show you what is the natural period of our building. Okay, so let us consider we have modeled our building, we have done everything, like self-aid is there. So model of there. Okay, so let's see this slide only. Okay, in this slide, SA by G is there. So we need to know what is the SA by G, what is the force acting on our model, seismic force acting on the model. For that, we are calculating AH, and for calculating the AH, we need to know what is the SA by G, right? So SA by G can be obtained from this plot. For that, see, we need to know what is the natural period T of our building. So code has given some from this is also from various researchers. Code has collated simple formulas for various kind of building based on only the height of the building. So if you know the height of your building, you'll be able to know what is the natural period of your building. Okay. Actually, the natural period does not depend only on the height of the building, but for simplicity, simplicity in practical design, code has given this time period. So time period can be obtained by, let's consider since we have model RC, reinforced concrete MRF, moment resisting frame. So time period can be obtained by this first formula, 0.075 h to the power 0.75, where h is the height of the building. Okay. So from here we can calculate what is the time period, and then if we know, let's consider the time period of our building is 1 second. Okay. Time period of building is 1 second. We can, from this x-axis, we can be able to calculate what is the SA by G. Now this SA by G can be used in this equation, and then we can able to use it for calculating SA by H. So now we know SA by G, we know Z by 2, and we know I by R. Okay, no, we do not know I by R. I is the importance factor, which is based on what kind of building you're designing, whether it's a hospital building, whether it's a fire station, or whether it's a very simple residential building. So based on the importance of the building, you will be able to assign a factor, some additional factor of safety. So this also can be, you can consider by yourself, or you can take from IS code. For example, let's consider hospital building. So we can assign the factor as 1.5. This will again increase your earthquake load. So more earthquake load means we are designing for higher load, right? So this is the importance factor. There is one more factor called R. R is the response reduction factor. So this is a very important factor. So response reduction, what it happens is, So since we whenever you design a building, when you're considering earthquake forces can be very high, and you may not be able to economically design your building. Okay, if you are designing a building for the entire earthquake load, your building sections can be very huge. Column sections, beam sections can be very huge. So for make it economical, we use response reduction factor, but that is not the only reason. The first and the foremost reason is for making the building economical. But see, you are not designing. Let's consider some level of earthquake is coming, and if you are not designing for that level, if you are designing for a lower level of earthquake, what will happen is your building may go in non-linear ranges, right? So what earthquake does is, earthquake let the building go into non-linear range if some earthquake occurs, but the design criteria are set in such a way that the building will go into non-linear range, but it will not collapse. That's why it's called special moment resisting frame. So this is a function of response reduction factor. You can read for more details, but since we have less time, so I want to proceed. So by using this, we can able to find what is the seismic coefficient. So from here we will be able to obtain what is the base shear. Okay, so once we know the base shear, what is the force acting at the base of the building, we will be able to distribute into the various stories. Okay, let me show you through a small example. So I've taken a simple example which I had created in the past. Here there's some simple properties are given, like what are the properties of concrete density, brick wall density, if there's any wall in your structure, floor finish, roof finish, everything. And from here we can know what is the number of slabs in the building. For example, in our model here we had 6 slabs in each story, 6 slab panels in each story. So I've given one example where there was 16 slabs. So sorry, number of slab, and then for each 16. Okay, so why I'm doing this, I'm obtaining what is the self weight of the structure. For that, I need to know material properties, I need to know sections, thickness, everything. Okay, so from here I have obtained I consider my building is having slab, some number of beams, some default sections, walls are there, internal wall are having thickness of 230. I'm assuming that there's no internal walls, because internal walls may be having 110 mm thickness or various thickness as per the requirement. Let's consider there are some shear wall also, and there's some live load. So based on that, I have calculated what is the forces due to various members, and then I found that total load at a typical floor section is 3263 kilonewton. Okay, and total dead load at the roof level is 2261. Now, why the dead load is very less at the roof level? Because in roof level, because in this while calculating load, you can directly calculate based on every member. See, this is if you see the elevation of our building, so the portion from half of the third story to its top, so that will consider the load acting in its top story. I'll show through one diagram. Okay, it's not clear here also. Okay, so let us consider this is how we calculate. So basically the live load at the upper floor will also be less, as well as we can see from here the total load at typical floor is 432, and then total live load at its roof level is lesser. So generally we do not have access to roof, so live load are very comparatively less, or half of the live load at other stories, and the dead load are also lesser at the roof level. Okay, now based on that, code has given a clause like, for obtaining a seismic weight, if the live load, now how to obtain the live load? Live load, I already told a few moments ago that live load can be obtained by using IS 875 part 2. So for various category of building, you will be able to know what is the live load we need to apply. So let's consider I have applied some live load as 3 kilonewton meter square for our conventional building. So code has said that for obtaining seismic weight, if the live load is also called imposed load. If the imposed load is less than 3 kilonewton per meter square, you need to add 25% of the live load to the self weight of the building. To the for calculating the seismic weight, 25% of live load will also be applicable. Now, if your live load is greater than 3 kilonewton per meter square, you need to apply 50% of the live load. We need to consider 50% of the live load into seismic weight as well. Okay, so this is where I have computed seismic weight as 9,000 kilonewton. Okay, so 9,000 kilonewton is the seismic weight of our building. Now we know, if we know the seismic weight, we will be able to know what is the base shear, what is the force acting at the base of the building. How? By using the equation VV equal to AH into W. Okay, so for calculating AH, we already saw that the equation for AH is this: Z by 2 SA by G I by R, right? Now, so importance factor I've considered Z.5, response reduction factor given by code as 5, and zone factor. Since I'm looking for zone 5, maybe Assam or some northeast states, so zone 0.5, building height, everything I've assigned. Okay, and then I've obtained base shear seismic coefficient as 0.135. 0.135 means the force at the base of the building is 13.5. The lateral force at the base of the building is 13.5% of the seismic load. Okay, that I calculate from the same equation, Z by 2 SA by G I by R. So based on that, VV, I've calculated the base shear VV equal to AH into W. So the base shear, the total force acting at the base of a building is 1200 kilonewton. Okay, now we know what is the force acting at the base of the building, but we need to distribute into various stories, like the diagram which I showed earlier. So this diagram. So we need to distribute the force acting at the base to its various stories. So code has from a number of study, code has found that for conventional RC framed buildings, the load variation at the roof level is parabolic. So if you go to the top, the lateral load increases. So this, using that, they have given an equation. So using this parabolic form, we can distribute this VV into the design lateral forces at the various story levels. So QI, I calculated QI is given by WIH square, where WI is the force at the typical floor, and from table 5 I have given vertical load distribution, where WI is the weight of the building. So for this 3-story building, we can see at the roof WI is comparatively less. H is from the base of the building. So for ground floor it is 3, for first floor it's 6, and for second floor it is 9. And then I used the equation for QI, and I obtained QI, what is the base shear at various roof levels. Okay, so using this, I've calculated what is the various roof forces applied at the various roof level. But if we'll see at a typical roof level. Okay, now before going to there, so I calculated what is the lateral force to be applied at various floors, right? Now the loads needs to be applied into its center of gravity, center of mass. Okay, center of gravity. Okay, so each floor is having different, each floor may have different plan. For this purpose, the plan is regular, so of course it will be exact, the center of mass will be exactly at center at all floors, but this may vary based on your building plan, which building plans of various story levels. So we can assign it into these points, right? Sorry, this we can assign it into these points. But for that, whatever the force at the roof level is there, we need to again redistribute into various number of joints. There can be a very large number of joints. So there's one method. What we do is, whatever the force which we have calculated, we will assign it into the CG of that particular floor. So CG is at this point somewhere here, but since we have made it a default model, there is no joint at that point. So what I will do is I'll assign a joint here. So if you want to know what is the coordinate of this point, so let us go to roof. Okay, so it is showing here as z equal to 9, which means I am at the roof. Okay, so I'll select this joint. If I right click, it will tell me what is the coordinate of this joint. The coordinate is -7, -5. Okay, and if I'll select the coordinate of this joint, this coordinate is okay. This is y, and this at this point the coordinate is y equal to 0, x equal to -5. Now if we'll see at the center, it is showing lines x and y, which means our origin or 0, 0 location is at this point, where we need to make one joint, because if you do not have joint, you will not be able to assign the load. So we'll make an additional joint here. Okay, so an additional joint can be obtained here, and we need to apply that is joint at this position. So what we will do is we'll assign the joint here. Okay, so okay, we have assigned an additional joint here, but what we need is we need to assign the joints at the various others level also, because we need to apply loads at not only at this floor, but we need to apply load at other floors also. So we'll select the here, and then we'll again replicate, or we can manually do that also. So since I have assigned this at the top floor, I can replicate again 2 number of times at the lower 2 floors. So yeah, so see, it came right. So it is again it has automatically highlighted whatever joints which was present earlier, right? So yeah, now see what this way we have created an additional joint. Why we have created? To assign some earthquake load. Earthquake load we have already calculated by using equivalent static method. Okay, now let us assign that load, earthquake load. So I've selected one roof, and then what we'll do is we'll go to assign, whatever assignment we do here from here. So we need to assign the earthquake load to the joint. So select that joint, go to assign joint load, and then forces. So what force we need to apply? We want to apply earthquake load at this joint. So earthquake, and then we want to apply, let's consider force in x direction. Okay, so let us consider we are using the same value which we have which is here. So at the roof we need to assign 665 kilonewton. So what we'll do is 665. Okay, it is kilonewton already. So we have applied some load. See, you may be able to see here 665 kilonewton. Okay. Okay. Now we'll go to lower floor, z equal to 6, and then we'll again select assign joint load forces. What forces we need to apply? We need to apply 446 kilonewton here. 446. Okay, and let's consider again. We'll go to z equal to 3, and then we'll assign joint load forces, and it was something around 110 kilonewton. Okay, so we have assigned earthquake load in a very simplistic manner by using equivalent static method. Now okay. Okay, I've applied dead load. Now let us apply live load as well. Okay, live loads are applied at the floor levels. We know that at roof some lesser live load is required, and at other joints, at other levels like first and second floor levels, we generally have higher lateral load. So let us apply same lateral load for simplicity for this purpose. Okay, so first we'll select all the slabs. So for shortcut in selecting, we'll use select tab. So select and then properties, because we have already defined some properties. So for selecting slab, what we'll do is we'll go to area section, and then in area section we'll select slab. So all the slabs we have selected, and then we'll assign what we are going to assign. We are assigning some area load. So we are going to assign in area load, we'll assign some uniform load, and then we'll go to live load. So we have assigned some live load, which is, let's consider we are assigning 3 kilonewton per meter square. Okay, So it is in gravity direction. So direction you can, if you'll put 0, you need to put -3. But since we are assigning gravity, it will automatically take into account that we are assigning the live load in downward direction. So yeah, so we have assigned live load also. Okay, so we have assigned in a very basic manner what is the earthquake load. Okay, so after you save the structure, you need to save the structure. You need to save it somewhere. Before analyzing, you need to save it somewhere. So I'm saving here. Okay. Okay, I've saved this building here. Okay, now we have made some combination. We have modeled the building, applied some loads, and then now we'll analyze the building. So we can apply other load also, but I'll show you how to analyze and how to check its load. Okay, so we'll go to analyze, and then there are various other options like you need to know, you need to consider, you want to consider what degrees of freedom. Okay, what kind of structure is it? A space frame, it's a plane frame. So we have a space frame. So for that, what we'll do is we'll go to ask for dead, or whether you want to run for earthquake as well. So based on that, we can toggle here. We can click here, and then we can change whether you want to run any specific load or not. So since we are running, if you want, since we want all these load cases, so we'll run for this. So run now. Okay, yeah. So see, we have analyzed the building. Okay, now it will show a very weird trend. See, if you will see that the joint we have created, the joint is in the air, and if you'll see the deflection, see, joint is not moving at all, and we have this deformed shape which we are looking at for dead, right? So for dead, obviously it is going to deflect in downward direction. So it is deflecting in downward direction. If you see the frame, it will also show like this. Okay, now, so what is the problem? Why it's not deflecting? Okay, why the joint was not deflecting? So why the joint is not moving with the flow? I'll give you the reason for that. See, the joint is not moving. Now let us, before that, let us consider understanding the joint. Let us see what is the deformed shape because of earthquake. Now see here, what's happening? The joint is only moving, the building is not moving, which means the joint we have created is not connected to our entire model. So what we need to do before any analysis, we need to connect it into a model. Because see, the load which we have applied at joint, but actually earthquake load is not concentrated at the specific joint. It will be distributed to its a specific flow. For that distribution, we use a function called constraint. There the thing which we applied at the base is called restraint. So similarly, we need to make a diaphragm at a particular story level. So for that, what we do is we consider the function constraint. So for that, what we'll do is we'll select we'll select the entire model except the base, and then we'll go to assign joint constraint, and in joint constraint we'll assign diaphragm constraint. So in diaphragm constraint, what we need is we want that every story level will need to behave as a single body. Okay, so we have, and then I'll tick this section, which means assign a different diaphragm constraint at different locations. So I did it, and then I'll assign this diaphragm constraint to the building. Now let me analyze. So I've saved the model, and then I'll go to analyze for all load cases. Okay, now we can see here it is moving in downward direction. Also, if you'll see XY, sorry, dead load. Yeah. Yeah, this is the dead load. Yeah, we can see again. Yeah, joint is since we have created the joint at that location, but now the earthquake load is distributed uniformly, and the not just the central joint, every joint is uniformly, every member or every portion of that member is deflecting. Okay, so this is how we will know that whatever we have modeled is correct. Okay, now see, this is the most basic kind of analysis called equivalent static analysis. Once we have created our model, we have analyzed the building, we need to know what is the design forces. So for that, how to do? There are a number of columns, and each column is subjected to various level of forces, right? So the most basic is select all the forces and find what is the maximum forces in any of the column. Maximum forces in terms of bending moment, shear force, torsional moment, okay, if there's any. So we'll select all of the column, and we'll find out what is in any of the column, what is the maximum forces. So if we know maximum forces, what we will do is, using that maximum forces, we'll be able to design, right, manually design. Similarly, for the beam, we design beam only for moment and shear. So we'll select all the beams, and we'll find out what is the maximum forces, maximum moment and maximum shear force in any of the member, and based on that we'll design. Okay, so I'll show you how to extract that force. So for that, let me select columns first, because design of column and beam are separate. So properties, and then frame sections, we are selecting columns. Okay, we have selected columns. Now I'll go to, since I want to display some results, so we'll go to display and then show tables. Okay, in show tables, I'll select that I want the forces for load combination. So since we have already created some combinations, so for this combination, it will show the load. We can also see for various other cases individually, but let us take these two cases. Since I'm showing, let me take only one load case. So for this 1.2 DL plus IL plus earthquake load, so I've selected that forces, and now the result will only be shown for that load case or that load combination. So since column is a frame, so I want to see frame forces. So I selected this one. Okay, now, okay, so from here we can see I have selected around 1, 2, 3, 4, 12, 36 frames. So for all this 36 frame, 1 to 36, it has created, it has given me all the forces. I can go and I can extract this to Excel, and then see for each force, each member. Let me show you only for member 1. Okay. Okay, for member 1, I can see the forces. What is axial force, shear force in both the direction, and the moment M2 and M3 in both the direction for the member 1. And see it, since we know that the forces in a particular member is not constant, like if you'll see the bending moment diagram for this member, because of this load, we can see the bending moment. This is the axial forces on the various member. We can also see the bending moment diagram. Sorry, yeah, this is the bending moment diagram. We can see the bending moment diagram. And from here, what we can know is the bending moment does not remain constant. As you already know, there's bending moment diagram, so it varies. So what software is doing, software is giving the forces at 3 locations, at the 2 ends as well as at the middle. Okay, so the same force we are seeing at the in this Excel sheet. Okay, so here it is seen here that the forces are varying. Minus indicate compressive force. Now what we can do is, if you want the most critical forces in a very simplistic manner, what we'll do is we can obtain what is the maximum forces P, V2, V3, M2, M3 out of all this. Okay, and then based on that we can design the building. Similar thing can be done for column. Okay, sorry, beam. This is for column. So column need to be designed for P, M2, and M3. So once you know P, M2, M3 as well as the shear force, you'll be able to design. Okay. So similar thing can be done for beams. So once you know what are the forces coming into the beams and columns, you are able to design. So from in that way you can manually pick up the forces and then you can design. Now, but we have assigned some initial sections, right? So we need to, if you want to check whether design is safe or not, we can go to design here, and then we can go to concrete design. So in concrete frame design, we can check change view references. Okay. So here we can change what code we want to design, for example, Indian code, and then it can ask number of PM interaction diagram. So, and if you want to consider any eccentricity, because if your building is not symmetric, the center of gravity maybe, or center of gravity may not be exactly at the geometrical center, right? So we need do we want to consider any eccentricity or not, as well as the factor of safeties. This is concrete 1.5. If you want to change anything else, so these are various factors. Once we know this, once we set this, we can start the design check of the structure. So it automatically checks and then gives some reinforcement at the various locations in this form. Okay. So since I've kept the unit as meter, so that's why it was giving something like that. Now see here, it has given some uniform reinforcement to all the columns, something 2000 mm square. Now similar is for beam, but it's varying. See, what we know for beam is, let me make the XY here, and then I'll show you the bending moment diagram, M3 for these load cases. If you'll see at this, at the corner, what we know is at the corner, the hogging moment are quite high, because of which the reinforcement at the top we need to provide are higher, and at the center the sagging moment are high, because of which in the central location the reinforcement is higher. It has made some reinforcement. It has given some reinforcement in mm square for that building. Okay. Now using these forces, we have obtained the design. We have obtained the design for what are the design reinforcements. Now we can also verify whether all members are passed, and it's showing that all concrete frame pass the stress capacity. But what it does is it does not change the section. So if you want to change the section, or if you want to change the reinforcement which it has not given, so what we need to do is we need to manually design it. That will be much better. Okay. So this is how we want to design, and using equivalent static analysis. This is what is done in conventional method. Some consultancies uses response factor analysis also, but time history analysis, no code nobody uses for conventional purpose for residential complex or commercial buildings. But if the structure is very important, people goes for time history analysis also. Okay, so here I've explained you how design is there, and also I've told you how linear model. So as of now, I have explained you how a linear model is created, how earthquake loads are assigned in terms of earthquake loads are calculated and assigned, and how basic design is created. Now this is where I want to conclude the introduction section. Okay, so yeah, this combination is all I also showed you. And if the structure is symmetrical, we need to consider some eccentricity, and rather than applying the forces at the geometrical center or center of gravity, we need to assign some eccentricity, and then we need to create some joint, and we need to assign forces at that point, and the response spectrum. So here I conclude the basic portion, the equivalent static analysis. And if anyone is interested in other analysis like response spectrum and time history analysis, I will explain you. But before that, let me cover the question which you have asked, and after that, those who are interested, you can stay in the seminar. You can stay in the webinar, and those who since we have already taken 1.5 hours, so those who want to leave, they can leave after question and answer session. Okay. and those who want to stay for response spectrum method, they can stay. Okay, so before that I want to take the question, like Anjan has requested me, can we design the complete elements of building SAP 2000 along with detailing as well? Of course, yes, since we have selected the code as IS456, and uh, we can, in spite of manual design, we can design it, creates a report, and it also gives a detailed reinforcement at what locations, and we need to apply. Yeah. So next question is, Kaza, is this presentation available? I don't know whether presentation will be provided to you or not. You can ask question in the chat. Okay. Another is the question by, any difference between stat pro? Yeah, the formulation is completely same. The process which I showed you, the for not just for SAP and stat for any analysis design software, the formulation is same. And so there are since these are for the product of various different companies, so they have their own way of there are way in the process, but the background is same for any software, not just stat pro and SAP 2000. For ETABS also it's same method. What happens in response spectrum analysis is we have a 3D building. Okay, in response spectrum analysis, what is done is the 3D building is broken into number of single degree of freedom systems, and each single degree of freedom system is analyzed separately, and then design forces, deflections, everything is obtained for each single mode, and then ultimately they are combined to obtain what is the overall force coming into the structure. So it is a form of there are various, like if you'll see this 5-storied model, I have shown it in a very simplistic manner. The structure is broken into 5 degree of freedom. I've shown here they are having different height, but it may not be. It is not actually. But it is the entire structure is broken into different number of modes. It can be 5, 10, 20, and we can also change the number of mode we want to consider in our structure. So based on the number of mode, it carries analysis for each mode. For each mode, it carries what are the forces, what are the deformation, and it does some model combination. It uses some model combination rules, and using that, it obtains, by combining, it obtains what are the overall force coming into the structure. So I'll show you the response spectrum analysis in SAP 2000 in very short, in a brief manner. So let us go to define, and then since response spectrum is a function of time period, so we'll assign some function. So we'll go to response spectrum and see there are various codes, right? So we can assign the plot directly from file. For example, okay, I've not opened some, I've not given file. Okay, so there was one response spectrum I had shown you, right? So yeah, this response spectrum is for as per Indian code, and it is irrespective of zone. So this spectrum analysis can be, this spectrum can be digitized in a table, like time period versus SFIG. Also, some equations are also given for this flat as well as some this parabolic portion in IS1893. You can use this, and you can create an Excel file for that, or else, since so from that Excel file we can read, and then we can assign, right? So if you have Excel file of that response spectrum, you can assign here, and you can directly carry out the response spectrum analysis. But if you do not have that, so what you can do is you can directly go to IS1893 2016, and then you can select here what is the zone, what is, since you can see the zone factor is changing as per the zonation zone factor which we are using. Okay, so Yeah, so zone 5 is 0.36. Importance factor you can change as for the kind of structure. Soil type, soil 1, 2, 3 are there. The type, what are the soil type you are considering in your region? Whether it's a soft soil, whether it's a hard soil, whether it's medium soil. So you can select that. I'm not going into very detail for here. And this is the response reduction factor, which I explained you earlier. So based on that, it creates a response spectrum automatically, the software. And uh, we need to provide a damping factor also, damping ratio also. So let's consider we have defined this as a response spectrum. Okay, so response spectrum is defined. So yeah, so meanwhile, let me, okay, the response spectrum is defined, and we need to go to load cases, and we need to create a load case for response spectrum also. So select, since we are doing response spectrum analysis, we'll go to load case type, and then we'll go to response spectrum method. And in response spectrum, we will select the RS as the response spectrum, which I had already assigned. Response spectrum analysis can be done in one direction, two direction, or multiple directions. So I'm only selecting U1 here, and the scale which code gives is in terms of SA by G. So SA by G which we are doing, G is 9.81. So whatever value it is showing here, for example, 0.5. The actual acceleration is not 0.5. The actual acceleration is 0.5 multiplied by G. So we need to give that factor here. So I've applied the scale factor 9.81 and I add. Okay. So if you want to assign some eccentricity to the structure, you can assign here. And then since I told you that the software, the method breaks your structure into number of modes, you need to select some combination rule, like how these forces are combined, how the deformations are combined after analysis for individual codes. So you can, since you do not know all these things, so I will not cover. Let's only select SRSS, sum of square root of squares, okay, square root of sum of squares. Okay, and then there are various other, but since I'm not going into detail of response spectrum, so you can skip that. Okay. So I've assigned one response spectrum function. So let's keep it name again as RS in X direction. Okay. So U1 is X, U2 is Y, and U3 is Z direction. So I've created response spectrum. Okay. And since I want to combine that again into make into combination, so in the way we have created only two load case, two combination like 1.2 DL plus LL plus earthquake load. Similar thing we can do for earthquake load also. So earthquake load lastly we assigned in terms of equivalent static load. Now we can assign in terms of response spectrum. So what combination will be there? The combination will be something like this. So let us make one combination, 1.2 DL plus LL plus response spectrum. So in spite of EQ, what we'll do is we'll select response spectrum along X direction. Okay, yeah. So this combination is created. Okay. Now the response spectrum analysis definition is completely done. There are a number of more complexity, like why only in X direction, why the earthquake is coming in only positive direction, why not in negative direction, what about the vertical earthquake component. There are lots of complexity, but before that I want you know all these basics. So if you know, you can explore much and then you can do yourself. Okay. So analyze, run analysis. In run, now what we are doing is we want to run for response spectrum case also. Yeah. Let us run for all. So since these are elastic analysis, it takes a few seconds to analyze your building. Okay. So analysis complete. Now we can also see the forces displayed. So table, and then let's see for this response spectrum only. Okay. So we have selected this response spectrum load combination, and yeah, again it shows. Let me change the unit first. You can change unit anytime here. So kilonewton meter. So display, show tables, and then from here we can select response spectrum, and then okay, yeah. So see here. Okay, what it happened was we didn't selected any member. So what it did was it selected entire member at once, beam as well as column, and then it gave the table of forces. Okay, so if you want the forces for only the columns, what we'll do is we'll select only the column. Okay, we selected column. Now the table will only be for the column. So here, frame forces, element forces, and we are looking at for only this. We can look for more than one cases also. Yeah, so this table is obtained, and this table again gives forces for let me export into Excel, and then I'll explain you more here from here. Yeah, so these are all the forces according to this load combination. We can also see here that now in equivalent static, the forces were showing only for three points. It's again showing only for 3 points, but there's one additional column which gives maximum as well as minimum forces, right? So why is it? Because what it in response spectrum analysis, what software it does is first it applies the earthquake load in positive x direction, and again it applies in negative x direction. So based on that, for the same member, we can see different forces. Once is the forces when we applied in positive x, and another when we applied in negative x direction, right? So in that way, we can be more sure, right? If we are doing equivalent static, we need to make multiple combination. In first one combination, we need to use positive EQ, positive earthquake load, positive x direction, and in another combination, we need to make negative. There will be large number of combination, but this is reduced by this complexity is reduced by doing response spectrum analysis, and there are also many things which I'm not explaining you here. So in the similar manner, in what we did in response equivalent static, we can obtain what is the maximum force P, maximum V2, V3, as well as maximum M2, M3, and then we can design our building, right? There are a number of other advantages in response spectrum analysis. So this is the basic thing of response spectrum analysis. The main point you need to know is in response spectrum analysis, we feed response spectra to the model, and what software does is it breaks the structure into number of single degree of freedom. It analyzes each single degree of freedom, and combines all the forces using some combination rules, and then it gives the combined result for that structure. Combined design forces for that structure. Okay. Now let me go to time history analysis. Okay. So I was asked few questions earlier in time history analysis, so I'll cover that also here. But before that, let me show you how to carry out time history analysis in SAP. So I'm again unlocking the model. So define, it's also a function of time. So time history, and then we can select from time history from file. Okay. Let me consider some time history. What is it? Okay. Okay, I have some time history. Yes, you can see here is a time history. So I have selected some time history, like which time history I selected, I will tell you. Sorry. Yeah, so I have selected one of the time history, like the name of earthquake is it's earthquake of 1935, Helena Montana earthquake, recorded in Coral College. Okay, and its direction is 180 from the north, and there are a number of points, and for each point varies by 0.1 second. So these are some earthquake recorded at some different regions. So what you can do is, in time history analysis, first of all we need the earthquake recorded at the various regions. For example, if you are doing analysis for Siliguri, we need to locate what are the probable earthquake, what are the past earthquake occurred in that region, and using that past earthquake, what we do is we assign to the model. But what earthquake we need to select, whether the earthquake which we are selecting are going to occur in the past or not, we need to see that also. Okay, so first, but we have, there are lots of earthquake data available in USA, as well as European countries are also having a number of recorded earthquakes. Okay, but in case of our Indian condition, there are very few ground motion, only 500 ground motions recorded as of now, and that also after 2016, the recording is not going in very proper manner. So for that, what we need to do is we need to take the help of ground motions for the help of earthquake which are recorded in the various other countries. Okay, so now what it's need to be done is there are few questions I was asked earlier regarding ground motion scaling. So this is the ground motion, this is the time history data which has occurred somewhere, but to make it into some make it to be usable for Indian scenario, what we need to do is we need to scale up. We need to scale that software to make it compatible to the response spectrum of Indian earthquake, right? So after scaling, whatever the time history data, time history which we are obtaining, we need to use that for response spectrum analysis. This is a complete different field of study, and it's a field of research. It's a field of research actually. So I will not cover in more detail. Okay. So here, if anybody is very highly interested in it, he can write me. I can give some data, or if he asks me a question, I can also reply in very good detail to him or her. So here I've taken, I've taken some random time history, and then I'm assigning some data. So this minus this 5 what I have given, why I have given is based upon the data I'm obtaining. So the data starts from 5th line. That's why I give 5, and in each line there are 5 data. That's why it's symbolized, and each data varies. Like the first data is at 0 second, the second data is 0.01 second. So the time step we need to apply here. Okay, so this is how we have defined our time history. Okay, now once it is assigned, let's give name to some name to this data. Let us write this as TH1. Okay, we have assigned a time history. Okay, now after assigning time history, again we need to create some time history load case. So what we'll do is we'll go to time history analysis, time history. What kind of time history we want? We want to do linear time history, non-linear time history, and there are so many things in it. Let's go to linear only. So since the time history which we have got, which we generally use is acceleration time history. So acceleration I've selected, and then in which direction? Let's consider U1 direction. Okay, and then TH1 direction. Sorry, TH1 is the time history which I assigned, and again the unit is in terms of G, so I'll apply the scale factor is 9.81. And if you'll see here, it has said that the data is at for 5093 points. So let me see the results at all 5093 points. So number of output time steps, and output time step size is 0.01 second. So this is how the basic formulation is done for time history, and there are various other things, but I may not be able to cover in this span of time. So let's do okay. Time history analysis, fine. Okay, now the same thing, we can make combinations, but if you don't want combination, if you want to only see the result of time history, let's see. So let's analyze this building. Before analyzing, I want to say few more things. That what happens in time history analysis is, so what we are doing is we are feeding time history data or acceleration time history data to the model. So at each instant of time, there will be some acceleration at the base of building, right? So that acceleration creates some force equal to mass by mass into acceleration. So some force is applied at some instant of time, but that force is changing, right? At any instant of time, this force is changing, and if the structure has gone in non-linear range, what happens is our initial structure was something, but when we have applied some force to that structure, some instant of time, some force has applied to the structure, the building will deform, and it will deform permanently. Once it deforms permanently, and when some additional force is applied, what happens is that the analysis will be carried out for the deformed shape of the building, not the initial shape, right? So what happens is that the load is applied with time, and the structure is not remaining same if we are doing if the structure has gone into non-linear range. So at each instant of time is the forces are calculated and the results are obtained at each instant of time. So from this time history data, what we know is we can know how the bending moment shear forces or other design forces are varying with time, and what is the maximum forces. So for that maximum forces, we can design the building, right? So let us see the time history analysis and its results. So we have already assigned some time history data. So let us analyze the building. So yeah, here I've analyzed the building, and we'll see the result for time history analysis. Okay. So deformed shape. Let's see the deformed shape first, and then THA, time history analysis, I've given the name. Okay. So see here, when time step equal to 0, time equal to 0, we have got some deformation, but this deformation is negligible. And when I'm starting the animation, it's not moving at all, right? Because there's no force. Like now if we'll go and then keep on increasing, so it is giving deformed shape for various other time steps. So we have 5093 time steps, right? Let me see what is happening in the structure. Okay, let's, since I think I've used the same time history, so let us see what's happening in around 38 second, how the building is deforming. Okay, so let's go here 30 second. Okay, so let me increase the scale of the deformation. Yeah, so I have it can also show the envelope, or you can see at any time, at any time instant, what is the force. If you want to see, we can see. I'll show you how to see that. But before that, let's see the envelope. So this is the envelope. Envelope means what is the maximum deformation at any instant of time in various members, and we can see the animation for that also. Okay. Now I think I can increase the scale again, or maybe automatic. Yeah, this is some scale, which is also automatic scale is around 50,000, and if you go to any joint, it shows the it shows what is the deformation occurred. So if I'm selecting mm, so we can see that in horizontal direction 0.02 mm deformation has occurred, maximum deformation due to the time history data which we have assigned. Okay, we can also create here we can also create the video of the analysis. So let us, I'm keeping it here. Let me see if it is there or not. Okay, so for what we need to create video, we will create video for time history analysis. Start time is this, and time is this. We can change the increment if you want to see small variation or large variation. Okay. Okay, so magnification we saw as 50,000, right? Okay, so yeah, we can see how the building is deforming with the earthquake. Right. So since okay, you saw that, right? So we can save that also. So see, this building we can see is after the analysis also in a very good shape. Why? Because we have not assumed that any non-linearity is going on. because of which after each instant of time it is returning into its initial shape, and then again analysis is being carried out, right? So this is how we need to carry out time history analysis. I have not gone to non-linear. Maybe in future we can meet, and again if somebody wants to know more about non-linearity, I can explain you. So this is how we can see the forces. Also we can see the time history of bending moments, like at each instant of time what is the bending moment in the various columns. Let me show you an example. So display, so plot functions, and then let me select a member. So I've selected one member. Let me select this ground story column. So display, show plot function, and then see this frame it's showing here. So I've shown frame, okay, but what is this frame? Whether it's bending moment, we need to check from here. So yeah, this is axial force. Okay, let me show you the let me create this as axial force. Axial force in column 1. Let me name column 1 is C1. Okay, fine. Let me create one more. Load functions, add plot functions, and then okay. Frame forces, yes, and then bending moment, okay, and then we need to know the number of element. So the element 1, that was element 1. So add new plot, bending moment, frame 1, okay, fine. Yeah, that this was bending moment. So let me give its name as bending moment. I don't know, modify, yeah. This is bending moment in column 1. Fine. Okay. Okay. So display, show plot functions. We need to know how bending moment is varying with time. So bending moment versus time. Okay. Display. So see here how bending moment is varying with time in the building. Okay, so this is how, if we are doing equivalent static or response spectrum analysis, it gives the maximum value of force. For that we need to design, but it's not very realistic. But most realistic is time history, and that too non-linear time. Fine.
Yes, the dam is from during process, but use dam the water will be evaporated in hot summer. So that way we have to do it immediately. So we can use dam and cover it.
Very good explanation of what of this thing. So yeah, so it is showing how time history is how bending moment is varying. I can also show you how axial force is varying in that column, and then yeah, it's varying like this, and for that maximum force we can design the structure. So this is how the axial forces can be seen, and this is the linear time history, and this is what we can do it. There are a number of things which can do in if we go to non-linear region. So I've given you a brief explanation of various methods by which we can consider earthquake load. You can explore more from here, and if you have any question, you can ask me, you can mail me. Okay, so this is how this is where I conclude my presentation. Okay, thank you for your time. Thank you for this opportunity. Thank you faculty members. Thank you Tapan sir, Malesa sir. Okay, thank you students. If you have any questions, you can ask me.
Ravi sir, can you share the contact number?
Yeah,
in the chat box so that participant can come.
My mail number,
or the mail ID.
Mail ID. You can use.
Mail ID will be better.
Yeah. Okay. Arasan has asked me one question, so I want to ask that question. Why we have to create target response spectrum in time history analysis? So the response spectrum which we saw for Indian code, see whatever building we are designing for conventional process, it should be code conforming. So code has said that we need to design for that response spectrum. Now if we want, so that design spectrum, we will keep that as a target for conforming the code, because code is again made from a number of researches, right? And that level of earthquake is going to come. Okay, so for that we need to keep a target, and based on the target we need to target as well as the earthquake load Uh, okay, so based on the earthquake occurred in the past, the response spectrum is made, and uh, if we know what is the amount of, what is the magnitude of earthquake and what is the distance from which earthquake is going to occur, we will be able to select a number of earthquake from various regions. Like maybe from USA, some earthquake has occurred. We can pick up that earthquake, since the earthquake records are not available in India. So what we do is, by picking the earthquake from somewhere else, we can scale that to match or to make it as the level of Indian code. We design the building or we carry out time history analysis. So that is the reason for creating target as well as matching. There's another question: how to check the accuracy of the result? Yeah, the only way of checking the accuracy of the result is through manual calculation. So if you will read the nonlinear portion as well as response spectrum analysis, you can do the manual calculation and check with the model. There's no other way. But if you have done the modeling correctly, and you can check for a few times, and you will be sure that yes, your model is correct. Yeah.